There we go. All right, so could we come up with anything in terms of electricity? What's the real difference between voltage, resistance, and current?
I honestly have no idea.
Okay. All right, well, so in terms of electrons, current is going to be how fast those electrons move, right? So the current either is going to go fast or it's going to go slow, right? We talked about in terms of your charging blocks, the small charging block does not allow for the electrons to flow through quickly, right? So it takes longer if you were to use the tiny one to charge an iPad. Dude, you're killing me. Anybody got a big block to help him out?
Yeah.
Oh, can you guys, can you give it to him, por favor? He definitely needs the big block. That small block's going to take way too long. Way too long. Luke, do you really have one?
Yeah.
Okay, Marla? Really? I'm not joking. He really is going to take him twice as long. Twice as long with that little block. All right, so current. Okay, so ladies and gents, how can I make the current go slower? Because I don't want to explode my phone. How can I make it go slower? Yeah, I can increase my resistance, right? So I can add some resistors, which would be an electrical component. And so I can increase that resistance so that not all that current is coming to my electronic device too fast to then blow it up, right? All right, voltage. Notice voltage. What is the difference between like a 1.5 volt battery and like a 9 volt battery?
The one has more voltage.
Okay, has more energy, has greater voltage, has a greater potential difference, right? So that means that the battery with the higher voltage is going to push the electrons faster. Push them a little bit faster. So when we look at this and we say, all right, voltage. Anybody know in our equation, we're learning a new equation today. What letter do you think is going to go with voltage?
V.
V. And then the units are? Nope. What was it? Volts. Good. All right. So you did find V equals IR. All right.
Oh, wait, it was that?
All right. So resistance in my equation is going to be what letter? R. Now, do you remember from the vocab, what are the units for that? Ohms. Which I can abbreviate ohms with this shape. Does anybody know what shape that is?
That's a Greek letter.
It is a Greek letter.
I don't know. Delta.
Omega.
How did I knew that. I didn't know what to say.
I can abbreviate volts with that V with the two little like arms sticking out kind of deals. All right. Current. So my equation, what's the final letter? There's going to be I. We already have too many C's. Remember, too many C's. All right. Anybody remember the units? Amps or amperes or amps or A.
Is there a fun Greek letter for that?
No fun Greek letter. You could just abbreviate with an A, though. That's totally fine. Okay? All right. So if I look at this picture, how many people have ever played with the hose when you're little? Everybody, right? Oh my gosh, I still play with the hose all the time today because my dogs love to play with water. Okay? So relate this to electricity.
Water moves out.
The electrons are the
Electricity
water.
flows.
Okay, the electrons are the water. I like that. Now, how can I make the water go faster or slower at my house? Yeah, okay, so I'm going to turn it on either a little bit, which would be a low voltage, which if it's a lower voltage, does the water go fast or slow? Slow. If I turn it all the way on, which represents my energy source, my voltage, it's going to move faster. All right, now how many of you guys were this kid that your parents are watering the flowers and you walk up and you're like sneaking, and you grab the hose and you go, doo, and it turns off, and then you run away like, I don't know how it happened. I have no clue how that happened. What does bending the hose in half do?
Resistor.
Yeah, that's your resistance.
4 for 4.
Right? If I bend it all the way, ladies and gents, is any water going to get through?
No.
Not really, right? If I gun it 100%, there's not going to be any flow of water. There's not going to be any flow of electrons, okay? So here's a cartoonistic approach to our Ohm's law. Think of, listen up, Kaylin, put it away. Seriously? Think of volts as somebody that's pushing you, right? If somebody's pushing you, barely pushing you, are you going to move really fast?
No.
No, but if they really start pushing you, you're going to move a lot faster. So the volts is the person that's pushing, right? Think of how hard they're pushing the electrons. Whereas the one in the middle, you have amperes. That's your current. Well, if I increase the resistance, so I make the area that it can actually fit through a lot smaller, would that be more or less resistance? More, right? If it's more resistance, are we going to be able to move through it as fast? No. So think of this also like there's a fire, and we got to get out of this room. We have one doorway. Are we all going to get out that door as fast as we possibly can? Or is there going to be like a little bit of a bottleneck? Will be a little bit of a bottleneck. You're going to get kind of bunched up there at the end, and so the flow of the kids out the room isn't going to be as great, right? Whereas, let's say that we had a garage door on the side here, and we need to get out. The door is bigger, right? More or less resistance? Less resistance. So you're going to get out a lot faster. So think about in terms of wires. Our wires, if it is really thin, more or less resistance?
More.
More. If it was bigger, there's more room for the electrons to flow through, right?
Yes.
All right. What about if the wire was short? Would that be more or less resistance? Less. If it was longer, more resistance, right? So in terms of electrons when we're flowing, we got to consider that when we are choosing our wiring materials. So again, our voltage, our units are volts. I can abbreviate it with the fancy kind of V. Think of it as how hard are those electrons being pushed, okay? A 1.5 volt battery is not going to be enough to get my car to go, right? I need a higher voltage battery. Your car has a battery in it, okay? So voltage, units, volts, current, units, technically is amperes or amps. That's how fast it's going to go. I can abbreviate amps with an A if I would like. Resistance, again, I can control the resistance. I can increase it or decrease the resistance based upon the materials I'm choosing. Certain materials, because they don't hold on to electrons as much, and there's more electrons that are available to flow throughout, are able to freely allow for that flow, which is really, really good, okay? Whereas insulators do not really allow for electrons to move through it. So there's no flow. The hose is completely kinked, right? Units there is ohms. Remember, if you want to not write out ohms, you could just do the Greek symbol for omega. Okay? All right, so help me out then. If I want the current to move faster, I could do what? If I want current to go up, I can either option 1, decrease the resistance, or option 2, increase the voltage, right? So when I'm looking at my equation is V equals IR. If I want to solve that specifically for I equals what? V over R. Well, that makes sense. V is on top of my fraction. If I put a big number on top of the fraction, it gives me a big number, right, when I divide it? So that makes sense. That's a direct relationship. I'm dividing by the resistance, though. If I divide by a really big number, it gives me an itty-bitty number, right? So that makes sense. It's an indirect relationship, right? They do the opposites of each other, okay? So there's certain things that we can actually control when we're looking at what device are we going to try to power, how am I going to be able to transfer energy from the wall into my iPad so that it actually does have charge so I can use it, right? So I want to use an actual device that's not going to cause my iPad to explode, right? The energy we get from the power plants gets cut down again by transformers in your neighborhood. Right? Those big green metal boxes that you'll see, those get cut down. And then it goes to your house as a lower voltage. Right? So when we're looking at that relationship, we can control current, we can control voltage, we can control resistance. Really, I can just change my battery or add more batteries if I want more voltage. Okay? So in my Ohm's law, V is volts, I is current, R is resistance. Okay? So the only one that people sometimes get stuck on is the current because it is symbolized with an I instead of a C. Okay? All right, so let's do a little bit of math really quick in our head. What's the resistance of a light bulb if it's connected to a 120 volt outlet and has 6 amps of current flowing through it? Well, my equation is V equals IR. Where does this one go? 120 V. 6 amps goes where? I. Right? So 120 equals 6 times R. Solve. What do I got? R equals 20 what though? Ohms or 20 omega. Ooh, that's a beautiful omega. Yes. So good. All right. Try this one. What's the current flowing through your phone if the phone battery operates at 6 volts and has a resistance of 12 ohms? Well, V equals IR. 6 volts goes here. 12 goes here. So 6 equals I times 12. Yep. So I equals 0.5 what though? Amps. So I can write it like that or 0.5 amps. Up to you. Okay. So the calculation for this unit really isn't that bad. Okay. We're not going to spend too much time on it just because it's V, I, and R and you're just solving for one or the other. Okay. Since you would just be dividing to solve off, there's nothing weird like when we had to do the change in temperature, put it in parentheses, do final minus initial, and then divide off. Don't have to do anything weird there with this, okay? The biggest thing I want you guys to be able to understand is the relationship between the three. So how can I get more current or how can I decrease the current? What would be the impact then on voltage or resistance and vice versa? Okay?